Okay, so now we're going to look at combustion analysis. Now, combustion analysis is probably new to you, but all it is it's a real-world application of finding the empirical formula. So what we're going to look at is an example from your notes, which is example 9, and it tells you that you have a 3.489 gram sample of a compound that contains carbon, hydrogen, and oxygen. So it's a hydrocarbon. Okay, when you have an unknown hydrocarbon, what you can do is you can combust it with oxygen to produce carbon dioxide and water. Now, all of the carbon dioxide is absorbed by the CO2 absorber, all of the hydrogen goes into the water, and that's absorbed by the water absorber. So this 3.489 gram sample gets combusted through, and it yields 7.832 grams of CO2 and 1.922 grams of H2O. What is the simplest formula? So what I did is I went through and I underlined key pieces of information. Okay, anytime you see numbers, it's probably going to be helpful, so you should underline it. So we know our mass of our sample, how much CO2 and how much H2O we have, and then the problem says the simplest formula. Okay, when I see the word simplest, I think empirical formula. So what this problem is asking us to do is, based on all of this information, find the empirical formula of this hydrocarbon. And so what we're going to do is we're going to take these pieces of information and we're going to have to figure some things out. So since this is combustion, we know that this unknown hydrocarbon, right, I used X, Y, and Z for our subscripts because we don't know them, is added to oxygen. Okay, it's combusted and it makes CO2 and H2O. So some things to make note of. All of the carbon from this hydrocarbon goes into carbon dioxide. Okay, so all of the carbon goes into CO2, all of the hydrogen goes into H2O. Okay, so we know that our carbon and our hydrogen only go to their respective compounds, where the oxygen is probably going to be split up between the two. So we know all the C, all the H. We need to determine this X, Y, and Z. So your thinking as you go through this problem is, first, you should use stoichiometry to find your grams of carbon that are in the carbon dioxide and your grams of hydrogen that are in the water. Okay? What we can do then is we have our carbon, we have our hydrogen. We can use those values along with the mass of our sample to figure out how much oxygen we have. Okay, so that's going to be the first thing that we're going to do, is use some stoichiometry. And then once we have our carbon, our hydrogen, and our oxygen, it's just like an empirical formula problem, right? Because then we have the masses, we go to moles, find the ratios, and that's going to be the combustion analysis problem. So what we're going to do is we're going to start with finding the amount of carbon, hydrogen, and oxygen. So what I did over here is I said all of my carbon comes from the carbon dioxide absorber. So the problem told us that we yielded 7.832 grams of CO2. What I did is I went from grams to moles of CO2. Okay? When in doubt, go to moles. So I went to moles of CO2, but I just need the carbon that's in that CO2. So I said, for every 1 mole of CO2, we make 1 mole of C, right? So when we have just 1 mole of CO2, we also just have 1 mole of C. Then I went to grams of carbon using the molar mass. What I found is we have 2.137 grams of carbon that we produced from this sample. Then I can do the same thing with the water, right? All of the hydrogen went into the water. So from the water absorber, we had 1.922 grams, okay, grams to moles of water. Now, this is something that's important to look at. For every 1 mole of water, we actually have 2 moles of hydrogen, right? Because it's H2O. So for every 1 mole, we have 2 moles of hydrogen. Then we go from moles to grams. Now, an important thing to note here that I made note of is we want just a single atom of hydrogen. We are not concerned that it's diatomic, right? All we want is a single atom of hydrogen. So for every 1 mole, it's 1.008 grams. When we multiply all of this and we divide, we get 0.2150 grams of hydrogen. So what we did is we found the carbon and the hydrogen from their respective absorbers. Now, when we want to find the mass of oxygen, we need to use the sample mass. Okay, that's carbon plus hydrogen plus oxygen. Use that sample mass and the mass of carbon and hydrogen that we found from above. That's going to give us our mass of oxygen, right? Law of conservation of mass. The mass can't go anywhere, so our carbon plus hydrogen plus oxygen is going to give us this sample. So the sample was 3.489 grams. I'm subtracting the carbon and the hydrogen, and what I found is 1.137 grams of oxygen. Okay, so now we have our mass of carbon, our mass of hydrogen, and our mass of oxygen. Notice in each of these masses, I went out to more than 3 significant figures. I went out to about 4 for each of these. Don't round until the very end as you work through these problems, just to reduce the amount of error. So now that I have the mass of carbon, the mass of hydrogen, and the mass of oxygen, do it just like a regular empirical formula problem, which means I take those masses and I go to moles of each. Okay, so once I have my grams of each, go to moles. Then once we have moles, divide by the smallest. Right, now it's just an empirical formula problem. You're trying to find the ratio. So I have 0.17794 moles of C, 0.21329 moles of H, and 0.0710625 moles of oxygen. Okay, that's my smallest number. So what I'm going to do is I'm going to find the ratio by dividing each by the smallest number. When I divide each by that smallest number, I get 2.5, 3.0, and 1.0. Now, do you notice anything about these numbers? One of them is 2.5, right? We can't round 2.5. It's not within 0.05 to round. So what I need to do is I need to take each of these numbers and I need to multiply it by something to get me whole numbers. Well, if it's 0.5, just multiply everything by 2. Remember, if you multiply one of the values, you have to multiply all of them. So 2.5 times 2, 3 times 2, and 1 times 2 is going to get me 5, 6, and 2, which means my empirical formula for this unknown hydrocarbon is C5H6O2. So that's how we go through this combustion analysis. Notice the only difference between this and the regular or the normal empirical formula problems is that beginning part where you have to actually determine the C, the H, and the O masses.